So as we continue on looking at how to implement a linked min heap, let's take a look at the remove function. So our remove function, first off, if we have an empty heap, then we're going to throw an empty collection exception because there's no way to proceed. Then the only element I'm ever going to remove in a heap is the minimum element, because that's what a heap is designed to do, provide the minimum element at any given point in time. So I'm going to go ahead and pull the element out of the root. Now at this point, I've got to replace the root with some other element. If the size is 1, then I have an empty heap and I can change everything to null. Otherwise, I need to figure out what the new last node is going to be. So before, I had to figure out which node that would be the parent of the new node. Now I'm trying to find what the new last node is because I'm removing the previous last node. So now I have to go to the next to last node. Then, once I get that node, I'm going to look to see if it's a right or a left child of the parent. Whichever one it is, I'm going to set that to null. I've removed that node. Then I'm going to set the root's element to the node I get from that old last element. So that element is now gone. I've set the references to it to null. And then I've gotten its element out. And I could do this above, but I can also do it here because I know what last node is. So even though the parents don't have a reference to it and it's out of the heap, I still have a reference to that actual node. Then whatever my new last node is going to be, I set last node to that. So now I completely have thrown away the reference to that old last node. And I call the heapify remove method, which works in the opposite direction of heapify add, where now I have some value at the top, and it's probably a big value because I pulled it off of a leaf. And I'm going to push that element down the heap until the heap property is maintained. And then once I've done all this, the heap's in good shape. I'll return the element that was stored at the root originally. So let's take a look at what needs to happen for our method to find the new last node. Here is a fairly straightforward case because the last node is 13 and its sibling is the new last node. But a more difficult case would be if we had a heap like this where the last node is 15. So we have to get all the way back to 13. The way we're going to do that is we're going to check to see, am I the left node or the left child of my parent? And here 15 is, 8 is as well. So now we're at 5. Now we're not the left child. So then, if we're not the root, we're going to switch to the left child of the parent and then go all the way to the right. Now remember, this is a full tree. If we have a node over on the right subtree of the root, then we know that there are plenty of other leaves in the left subtree of the root at the same level. If we have a case that looks like this, then 12 is a left child. So we go to 6, and then again we do the same thing. We swap over to 4, 7, and then 11. And in the different case, here we have 9, the only node on its level. So it's a left child. So what we need to do here is go all the way to the root, find its the root's right child all the way to the right. So here's what that'll look like in code. We get the result as the last node, and this result is going to be the node we return as the new last node. In fact, why don't we go ahead and refactor that? So then, while we're not at the root, and while we're our parents left, we're going to go and get the parent. And if we're not at the root, we're going to switch to the left subtree. Then we're going to go all the way to the right. And that's what we did in the example. And once we do this, we'll have the last node, the new last node, and we'll be able to return it. Now, once we've removed that node, remember we swapped the root element with whatever was in that old last node. So now we have to readjust the heap to make sure that the heap property is satisfied. So to avoid having to call get left and get right over and over, we're going to create some variables for the node we're looking at, its left and right children, and then we'll have a next to keep track of where we need to try on our next iteration. So if there's no children, then the next is going to be null. If there's one child, then we're going to set next to the left child because that's the only child that there could be. There's no case in a heap where you would have a right child but not a left child. Otherwise, we compare the two children, and that next node is going to be the smaller, or the node that holds the smaller element. Then we're going to have this loop, and we're going to use next to go further and further deeper into the tree, each time comparing the element at next to its two children. And once we do that, we'll pick the smaller of the two children, swap that, and then move down one more level. And we keep doing this over and over until eventually we have a case where we're looking at an element and it's less than the element that we pulled off that last node. And in that case, we set that node's element to that value. And that would be the value stored at the original last node. And the last method we want to look at is find min. That's pretty straightforward. We just have to throw an exception if the collection is empty, but otherwise we just return the element stored at the root because the root will always have the smallest element.